we are eager to see any new results that is going to show us.
Okay, can you hear me?
Yes, yes, loud and clear.
Okay, thank you. Okay, yes, so today I would like to talk about the CLASP first result. So this presentation is based on our recently published paper in Science Advances. Just a moment. Okay. So then let's move on. Okay, so first let me explain about our CLASP experiments. So by the way, do you see the second page?
Yes, it's going well.
Okay.
So far.
Okay, thank you. Okay, so the aim of this experiment is to demonstrate the capability of the UV spectropolarimetry. Why UV? Of course, we want to observe the magnetic field in the as high as possible in the solar atmosphere closer to the corona. Okay, sorry. So then in the CLASP 2015, we measured line alpha, IQU spectral. So Q and U are linear polarization signal, then which are dominated by the scattering, and because probably that we also have a Hall effect. In CLASP2 2019, we measured IQUV spectra in the magnesium H and K lines. So in the case of the magnesium H and K lines, in addition to the scattering and Hall effect, by measuring the circular polarization signal, we are able to measure the longitudinal magnetic fields through the Raman effect. So this is a big advantage of these spectral lines. So this is one big motivation that we change the wavelength from the line alpha to the magnesium H and K for the CLASP2. So this is our instrument. So we modify the CLASP instrument like this. So the red character shows what we modified from CLASP1. So the instrument consists of the three parts: the telescope and the slit-jaw optics, and then the spectral polarimeter. So the optical layout is quite simple because we would like to maximize the signal to noise ratio. For that, we minimize the number of optical components. And the great thing here is working as the beam splitter as well. By doing so, we are able to measure two orthogonal polarization states simultaneously. So the spatial resolution is about 1 arcseconds, and the spectral resolution is 0.01 nanometer. Then the slit length is about 200 arcseconds. Then for the slit jaw, we kept the CLASP1 slit jaw optical system. So in the slit jaw system, we make observation of the line alpha imaging at a very high cadence of the 0.6 seconds. Okay, so in the CLASP observation, first we observe the disk center in order to confirm the instrumental polarization is negligibly small. Then we move to the Plage to perform sit and stare observation for 2.5 minutes. Then after that, we finally move to the quiet sun near the limb. So as you see in the lower right panel, this is the CLASP slit jaw images. And the surprisingly pointing is very, very stable. For example, the jitter is less than 0.1 arcsecond peak to valley. So actually we found that this is mainly caused by the rotation of the PMU, so wobbling. So the stability is quite good. So this is very important for the high accuracy polarization measurement, even though we perform the dual channel demodulation. So in this talk, I'd like to focus simultaneously observed by iris. So here is again, the left panel shows the CLASP slit jaw image, and the middle panel shows the iris image. And as you see, these two slits are very good overlap. So by looking at the iris dataset, we are able to see how the chromosphere are structured in this Plage region. In addition to that, iris data were also used for the calibration of the CLASP2 dataset because we are essentially taking the observation along the near wavelength range of the magnesium H and K line. Okay, then this is the CLASP2 data. So the slit is located at the edge of the active region. So most of part observing the Plage bright region. However, in the one edge here is observing the enhanced network region, as you see in the CLASP2 switcher image. And the right panel shows the temporally averaged IQU wave spectra. So Q and U is a linear polarization signal, then which is dominated by the scattering, and most likely because of the strong magnetic field of the Plage, the Hahn effect and the magneto-optical effect would happen. But here I don't talk about that. So here I would like to focus on the circular polarization here. So the magnesium 2K and the 2H are primary targets, and then as you see, the circular polarization signals are very, very strong. We clearly detect the circular polarization signal. And another surprising is that we also have several spectral lines showing the significant circular polarization. So one of the prominent ones, the manganese line here, identified by the red boxes. So we found that these manganese lines are originated from the lower chromosphere. So by combining these spectral lines, we are able to observe the magnetic field from the bottom of the chromosphere up to the top of the chromosphere. Okay, so lower panel shows the example of the profile. So from the left to right, the circular polarization of the magnesium 2K and the magnesium 2H and the 2 manganese line. So for the magnesium 2H and K lines, it shows 4 lobes. So very strong external lobes, which correspond located in the wing part of these lines. And we have a small lobes located in around the line core of the magnesium H and K lines. So we separately treated these lines, and the external lobe and the internal lobe were separately performed the fitting. Manganese line, it shows a very simple 2 lobes VOY signals. So in order to perform the fitting, we applied the weak field approximation. So weak field approximation is shown with a very simple equation. What we need is a circular polarization and the derivative of the intensity. And using this equation, we are able to derive the longitudinal magnetic fields. So the main assumption of the weak field approximation is the magnetic field is constant along the line of sight. Nevertheless, we are able to get the very reasonably good fitting as shown with these colored line. Then what we observed here in the top of the chromosphere, the magnetic field strength about 300 Gauss, and the middle of the chromosphere slightly larger of the 325 Gauss. In the manganese, lower chromosphere, it shows the 500 Gauss, relatively strong magnetic fields are derived. In addition to this observation, we also succeeded in the simultaneous observation by the Hinode SOT. Of course, as you know, Hinode spectral-polarimeter provide us with the photospheric magnetic fields by measuring the IQUV spectra in the iron line in the visible range. So using the level 2 data, we obtained a longitudinal magnetic field as shown in the right panel. Of course, the spatial resolution of the Hinode is too good, so we spatially smear to be compared with the CLASP2 data. By doing so, we finally derived this plot. So horizontal axis shows the distance from the slit center, and the vertical axis shows the longitudinal magnetic field strength. The lower panel shows the zooming of the upper panel. Then the green line shows a photospheric magnetic fields obtained by Hinode spectro-polarimeter. Then blue, black, and red shows the magnetic field in the chromosphere from the lower, middle, and the top chromosphere. So in the photosphere, as in the photosphere, magnetic fields shows a very high spatial variation like this. However, in the chromosphere, spatial variation is so small, smoother, and the field strength is much weaker. And interestingly, where we have a relatively weak magnetic field on the photosphere, in the chromosphere, we have a relatively non-zero magnetic field, and this field strength is very comparable in all the chromospheric layers. So that we think that the magnetic field is very concentrated on the photosphere. However, in the chromosphere, the magnetic field flux tube is suddenly expand, as shown in this figure. Okay, then we also check the correlation with the intensity. Intensity is a K3 intensity or K2V intensity of magnesium K line, so which indicates some information of the upper chromosphere. And we compare the intensity and with the magnetic field at these different heights of the magnetic field information. Then we found that the higher correlation coefficient in the upper atmosphere, like this. By stimulated by this finding, we also try to derive the thermodynamical properties from the intensity profile of the magnesium K lines, magnesium K lines, using the IRIS square database. Then we found that the product of the temperature and electron density near upper chromosphere also shows this kind of the properties. So this high correlation between the intensity or electron pressure and the magnetic field at the top of the chromosphere indicates that the magnetic field is a very important for the heating the chromosphere. And let's move on to the outside of the Plage. So here we focus on the enhanced network region. In this region, in the photosphere or lower chromosphere, we found a very significantly strong magnetic field. However, in the top of the chromosphere, magnetic field is almost zero. The right panel shows the example of the profiles. And as you see, the manganese or external lobe of the H line clearly indicates a strong magnetic field, the presence of the magnetic field. However, the line core shows a very small V over I. What caused this? So one possibility is that the intensity change, then this causes a cancellation of the magnetic field. However, this right panel shows a movie of the intensity or derivative of the intensity. Then we found that the derivative intensity is highly dynamic. However, it does not change the sign. So this means that the V over I is not canceled out by the intensity itself. So then it indicates that we don't have there is no magnetic field at the top chromosphere. So there are three possibilities to explain these. First one is the magnetic fields do not reach the top of the chromosphere and return to the photosphere. The second one is the magnetic fields become too weak at the top chromosphere, then we cannot detect the signal. The third one is, of course, what we observe is the line of sight components, so the direction becomes perpendicular to the line of sight at the top of the chromosphere. So we cannot find which is better, but what we can say is that the well-known wine glass canopy model is too simple to explain the observation of the enhanced network field. Okay, so here is the conclusion. So combining with the Hinode observation, we are able to obtain the magnetic field information from the photosphere to the top layer of the chromosphere. Then we are able to observe how the magnetic field connect from the photosphere to the top of the chromosphere. We also obtained the empirical evidence that the heating of the Plage chromosphere is of magnetic origin. And this presentation is focusing on the Plage observation, but the further CLASP2 result is the center-to-rim variation, the scattering polarization, polarization calibration, temporal variation that V over I will come in the future, in near future. Then finally, let me talk about our next step. So now we are planning the reflight of the CLASP2, CLASP 2.1. In this reflight program, we will not modify the instrument. We just fly the CLASP2 instrument. But by changing the operation, we will perform the scan. Then we obtain the 3D maps of the solar magnetic fields. So proposal was accepted by NASA, and we expect a launch in this year. That's all. Thank you.
Thank you, Dr. Ishikawa. Congratulations on the very fascinating results, and also congratulations on the reselection to fly CLASP2. Excellent, excellent work. We have one quick question from Valentina Zarkova. Ryohko, a nice talk, and challenging instrument. Lyman alpha line is normally very optically thick, and its wings outside flares are affected by partial redistribution of photons. How these effects change the magnetic field that we measure from Stokes parameters of the Lyman alpha line?
Okay, so first of all, what we measure in this observation in the CLASP2 is the magnesium H and K line. But of course, the magnesium H and K line is also the similar that we have a strong influence of the PRD effect, I think. Then I think that especially in the wing, because of the PRD effect, we have a relatively strong scattering polarization because of the presence of the PRD effect. And then according to the theoretical calculation, we have a, the magneto-optical effect affects the scattering polarization due to the presence of the magnetic fields. So we think that the magneto-optical effect also will be a kind of the diagnostic tool of the magnetic field. Of course, sometimes the interpretation is not so simple because the modeling of the PRD effect is very difficult and scattering polarization also difficult to interpret. But we think that the Harney and the magneto-optical effect also will be an interesting tool to investigate the magnetic field in addition to the Zeeman effect.
Got it. Thank you so much for the explanation. A very quick question from Dr. Brigitte Schmieder. What is your inversion code?
Okay. So in this presentation or in this work, we didn't perform any inversion. I said the fitting, but we just performed the weak field approximation fitting.
Correct. Mm-hmm.
Yeah.
Excellent.
So applying the inversion code is the next step. So our collaborators are also working on the development of developing the inversion code. So next step, yes.
Excellent. Great job to the entire CLASP2 team, and we'll look forward to the next awesome results from your experiment. We have to move on to the next speaker.